Hello, Geometry crew. Today we have day 5 in our SAT unit where we're going to be going over problems within triangles. This is just going to be just like our triangle chapter that we already had, chapter 9. So we're going to review some problems before we get into the next day, which is going to be focusing on SAT problems about triangles. So let's get started here. You're going to see just a natural progression just like we had during our triangle chapter from question to question here. So we're going to start on the first one. We need to find the missing side of the triangle where we have 2 sides out of 3 in the right triangle. Whenever we have 2 sides out of 3 in a right triangle, we can set up Pythagorean Theorem. We wrote that as c squared equals a squared plus b squared, where c is the hypotenuse. That's that side that's opposite that right angle. And then the other 2 sides are the legs, so we can call that A and B. Now let's substitute what we know. So A is 5, B is 12, and C is just X. That's what we're looking for. All right, so from there, we could just do 5 squared plus 12 squared. 5 squared is 25, 12 squared is 144. If we add those two together, we get 169. Take the square root, we get positive and negative 13. But the only one that works in this context is the positive 13. So that's 13 feet for that hypotenuse. All right, if we go down to number 2, this time it says leave your answer in simplest radical form. All right, so we're going to just go over simplifying our radicals again. Once again, Pythagorean Theorem, c squared equals a squared plus b squared. Where what we're looking for is the hypotenuse. So we have x squared equals, now you can call that a and that one b. And if so, we've got 10 squared plus 5 root 2 squared. Now remember, we need to put this full quantity in parentheses. All right, if we don't put that full quantity in parentheses, what we're actually squaring isn't all of what b is. All right, so we got to square this whole thing. Whatever b is, we got to square that thing. So 5 root 2, that quantity squared. 10 squared is 100. All right, for 5 root 2 squared, all right, 5 squared is 25. The square root of 2 squared, those just undo each other. So we have 25 times 2, which is 50. So we could just write x squared as 150. Now when we take the square root, we're going to get the square root of 150, which is something that we got to simplify. How you want to do this is up to you. We've used our factor tree before, and we can either take out the lowest primes or we can take out the biggest perfect square. The easiest one is going to be taking out the biggest perfect square. All right, so if we know our perfect squares, we know 25 is a factor of 150. And 25 times 6 is 150. All right, so when we take the square root of 25, we get 5, and the square root of 6 is simplified. All right, this has no perfect square factors within it. So x equals 5 root 6. Awesome. Let's move on to the next two. I'm going to clear the board and scroll down. All right, if we take a look at 3, it says find the area of the triangle. Now these are set up to be multiple step problems here, okay? Because likely in the scenario of the SAT, we would have multiple step problems for these area problems. All right, so one thing that we notice is that the hypotenuses of these right triangles is 12. All right, this one's rather simple. All right, if these 2 sides are congruent in both of these triangles, obviously that third side has to be congruent. We've got HL right here in both of these triangles, so that means that's 9. So we've got the full base for this triangle, which is helpful when finding the area. Now we just need the height. Well, to find the height, we could just take a look at this right triangle and use Pythagorean Theorem again. All right, so that's what we're going to do. So we've got c squared equals a squared plus b squared, where c is 12. We can call a x and b 9. All right, so from here, if we solve for x squared, we'd have 12 squared minus 9 squared, which would give us 63. And notice this says round intermediate values to the nearest tenth, and then round your final answer to the nearest tenth. So we're actually going to round this value. So when we take the square root, we're going to round this to the nearest tenth, which is 7.9. And now let's find the area. We have the height, we have the full base, which is 18. So for a triangle, the area equals 1/2 base times height. If we do that, we get 71.1 units squared. If we take a look at number 4, we're going to have one additional step here. So right now, if we take a look at this right triangle, the right triangle on the right side, we only have one side. All right, that's not good enough to find these two side lengths. In the left triangle, we've got 2. So we can find this side length using Pythagorean Theorem. So that's the first thing that we're going to do. So if we set up Pythagorean Theorem for that left triangle here, we'd have 10 squared equals x squared plus 9 squared. All right, then from there, 10 squared is 100, minus 9 squared, that would be minus 81, which would give us 19. And when we take the square root and round to the nearest tenth, we get 4.4. Now, I know it's not common practice. Usually we'd use that exact answer and then help use that to help us find the area and other side lengths if necessary. But we're actually going to use the rounded answer here for that side length because it tells us to. All right, now we got to find, since we know this is 4.4, we've got to find this side length now. All right, so once again, use Pythagorean Theorem. So we've got 6 squared equals, and I'm going to call this y since I called the other one x, y squared plus 4.4 squared. All right, so 6 squared minus 4.4 squared would be 16.64. Take the square root, and we get approximately 4.1 if we round that to the nearest tenth. All right, so that's helpful because now we can find the full base of that triangle, just 9 plus 4.1, which is 13.1. So now the area is 1/2 the base, 13.1, times the height, 4.4, and now we can find the area. And that would be 28.8 units squared. Awesome. In 5 and 6, this is utilizing the converse of the Pythagorean Theorem to state whether the triangle is acute, obtuse, or right. So now we just want to figure out, is c squared equal to a squared plus b squared, less than or greater than a squared plus b squared? All right. If c squared is equal to a squared plus b squared, it's a right triangle. If c squared is less than a squared plus b squared, it's acute. And if it's greater than a squared plus b squared, it's obtuse. All right, so all we got to do is identify our c, which would be the hypotenuse. Okay, that one's the hypotenuse there, supposedly, if this is a right triangle. And we can call the other ones a and b. So now let's set it up. And instead of writing equals, that's a 1 there. Instead of writing equals, we're going to just put, let me undo that. We're just going to put a little line underneath, a little blank spot. So 195 squared on one side and 170 squared, sorry, the square root of 170 squared plus 9 squared. All right, if we square this, we get 195. All right, let's square both of these. That's 170 plus 81, which is 251. So 195 is less than 251, and this is talking about c squared here. So c squared is less than a squared plus b squared, so this is an acute triangle. Now if we take a look at 6, we're going to do the same thing. All right, here is our value of c. If it's not apparent what the value of c is, we just got to find the longest side. So figure out what these are, and the longest side is going to be what you call C. And then you could call the others A and B. All right, if that's the case, we've got 15 squared on one side, and then the quantity 3 times the square root of 21 squared plus 6 squared. 15 squared is 225. All right, 3 times the square root of 21. If we square that whole value, that's 9 times 21. So that's 189 plus 36. Right? 189 plus 36 is 225. So we see that c squared equals a squared plus b squared. So this is a right triangle. All right, once again, going to clear the board. We're going to move on. All right, number 7 is not absolutely necessary in terms of the SAT, but we're going to go over it anyway. This is something that we talked about. State if 3 numbers can be the measures of the sides of a triangle. It's actually really simple. As long as C is less than A plus B, all right, then it can form a triangle. All right, not necessarily a right triangle. It could be obtuse, acute, right, doesn't matter. As long as C is less than A plus B, then that thing can form a triangle. All right, so the sum of the 2 legs has to be greater than what would be the hypotenuse, or that third side. So in this case, we can just label them A, B, and C, C being the longest side. All right, now we just want to double check, is C less than A plus B? Well, 6 plus 5 is 11. 11 equals 11. It's not, 11 isn't less than 11. So that would be a big old no. This cannot form a triangle. All right, now something that is very likely to be on the SAT, at least from some of the examples that I've seen, is things that talk about special right triangles. So all these are special right triangles here. We've got 2 45, 45, 90 right triangles, 2 30, 60, 90 right triangles. So we need to find the missing side lengths in these right triangles. So if we take a look at 8, the ratios for 45, 45, 90 is 1, 1, root 2. And if you don't remember what that means, all that means is if we have the short side, okay, or one of the legs in this 45, 45, 90 right triangle, we can get that side that's opposite the 90-degree angle, which is the hypotenuse there. We can get that hypotenuse by multiplying that leg by root 2. All right, so here's one leg. And this also means that the 2 sides that are opposite the 45-degree angles, those 2 sides, are going to be congruent. So that means y is automatically 9 root 2 on 2. All right, and then to find x, all we have to do is multiply this quantity by root 2. All right, sometimes this gets a little tedious. All right, first thing that we could do is multiply root 2 times root 2, and we would get 2. So that's really just 9 times 2 divided by 2. But then we have 2 divided by 2, and that cancels out, and we get 9. So x just equals 9. If we take a look at 9, we're starting with the hypotenuse. We got to get back to the leg. All right, so if we're starting here and we got to get back to one of the legs, we have to divide by root 2. All right, so 2 root 3 over 3. Now divided by root 2. All right, instead of taking this whole thing and dividing by the square root of 2, instead we could multiply by the reciprocal, which would be 1 over the square root of 2. That's the same thing as dividing by the square root of 2. It still goes in the denominator, okay, representing division. All right, but then the trouble is in simplifying. We have 2 times the square root of 3, all on 3 times the square root of 2. We got to get that radical out of the denominator. All right, so we're going to multiply by root 2 over root 2. We'll see some interesting things happen here. All right, so when we do that, obviously root 2 times root 2 is just 2. All right, so we have 3 times 2 in the denominator, which is 6. And then in the numerator, square root of 3 times the square root of 2 is the square root of 6. But we can still simplify this. Notice we have 2/6 here. All right, we could take out that common factor of 2, and we would get root 6 on 3. Okay, or 1/3 times root 6. All right, so in this case, both x and y, since those are the legs of this 45, 45, 90 right triangle, are both going to be the square root of 6 on 3. All right, let's take a look at 10. Now we have a 30, 60, 90 triangle. I'm going to do this in a different color. There we go. For 30, 60, 90 right triangles, the ratios are 1, root 3, and 2. And once again, this just means that if we have what's going to be the short leg, we can find the long leg by just multiplying by root 2. If we have the short leg, we can find the hypotenuse by just multiplying by 2. All right, if we have either one of these things, we have to divide by this quantity to get back to that short leg. So in this one, we've got the long leg. How we know we have the long leg is the 30-degree angle is always opposite the short leg. The 60-degree angle is always opposite the long leg. The 90-degree angle is always opposite the hypotenuse. So this is the long leg here. So to get the short leg, we got to divide by root 3. All right, so we have 9 root 3 on 2 divided by root 3. Once again, let's multiply by the reciprocal. Now when we do that, notice we have the square root of 3 in the numerator and denominator, so those cancel out. So we just have 9/2 for y. 1 second as my headset is running out of battery. There we go, and we're back. Now that we have the short leg, we just have to multiply by 2 to get the hypotenuse. So if we multiply 9/2 by 2, just to show some work here, once again, we have 2 in the numerator, 2 in the denominator. Those cancel out, and we just get 9 for the hypotenuse. All right, when we're taking a look at number 11, we're starting with the hypotenuse. So always, if we're starting with anything else other than the short leg, we can just divide to get back to that short leg, because it's always easiest to start with the short leg. So if we have the hypotenuse, we're going to divide by 2 to get back to that short leg. So in this case, we're going to divide by 2, and we just get v equals 2. Easy peasy. Now that we have the short leg, we can just multiply by root 3 to get the long leg. So 2 times root 3 is just 2 root 3. And boom, we're done. All right, so that's Pythagorean theorem, converse of Pythagorean theorem, and our special right triangle ratios. Everything else, for the most part, is going to be using those trigonometric functions that we talked about. All right, so once again, going to clear the board. Let's move on. All right, and these state, find the value of each trigonometric ratio rounded to the nearest 10,000th. All right, so in the first one, all we got to do is type that into the calculator. That's it. Okay, just make sure it's set to degrees, because it's using degrees here. The tangent of 39 degrees, if we type that in, we'd get 0.8098. And remember what these things represent. These things are ratios between two sides in a triangle. Okay, so we're talking about a triangle that is a 39-degree angle. We're talking about a right triangle that has a 39-degree angle. Let's say that's right here. And it's the ratio between the opposite and the adjacent side. Okay, that's what we're talking about. All right, let's take a look at 13. So cosine of Z. If we want to set this up, we got to know what cosine is. So we can always use SOHCAHTOA. All right, so cosine is the ratio between the adjacent and the hypotenuse. All right, so if we're sitting at Z, the adjacent side is going to be 18. Remember, it's always easiest to label that hypotenuse first, because in every example, the hypotenuse is going to be opposite that right angle. So here's the hypotenuse, and that means the adjacent side, which means right next to, is going to be this side. All right, not the hypotenuse, but the other one that's right next to it. So cosine of Z is adjacent over hypotenuse. And this does say round to the nearest 10,000th. So that means if we're not simplifying this fraction, we're just going to type that thing into our calculator, and that's what it would be to the nearest 10,000th. All right, if we take a look at 14, the tangent of A. So tangent is the TOA part in SOHCAHTOA. All right, so the tangent is the ratio between the opposite and the adjacent side. So it's with respect to A. So if we're sitting at A, the opposite side is going to be 30. The adjacent side is not the hypotenuse, not this one, all right, but this one, at 40. So tangent of A is going to be opposite over hypotenuse. And once again, if we round this to the nearest 10,000th, we get 0.7500. And then finally for 15, sine of C. Right, with respect to C, right, sine is the ratio between the opposite and the hypotenuse. Here's the opposite side, hypotenuse. Right, so sine of C is 15 over 17. And let's type that into the calculator. And we get 0.8824. Awesome sauce. Now we're going to be using these ratios to find missing angle measures and missing side lengths. Oops, didn't mean to do that. There we go. All right, so we got one talking about find the missing side, the other talking about find the missing angle. All right, and this is the whole point. All right, this is the whole point of these trigonometric functions. We want to find missing measures, things that we don't know in these right triangles. All right, so if we take a look at 16, we're given an angle, we're given a side length, and we've got to find this other side length. So we have to figure out what do we use, which trigonometric ratio do we use, okay, based on these two sides. With respect to this 24 degree angle, x is the opposite side, and 11 is the hypotenuse. So that's O and H. If we scan through SOHCAHTOA, O and H refers to sine. All right, so we got to use sine. Sine of 24 degrees is x over 11. And then we just have to solve for x. All right, to solve for x, we'd multiply by 11 on both sides. So 11 times the sine of 24 degrees is going to be 4.5 if we round that to the nearest tenth. All right, final question in this review. Number 17, let's find the missing angle measurement. So here's the angle that we're looking for. With respect to that angle, 29 is the opposite side. 21 is the adjacent side, because the hypotenuse is this one. So we have to use opposite and adjacent. Okay, that refers to tangent there. The O and A in TOA is tangent. So tangent of that angle, theta, is 29 over 21. Now to find theta, we take inverse tangent of both sides. Inverse tangent gets rid of this tangent. So really, theta is just inverse tangent of 29 over 21. And we get 54 degrees. All right, folks. All right, those are the bare essentials to get us started on those SAT problems. So in tomorrow's lesson, we'll go over SAT-specific problems that use trig that we could do sophomore year here. All right, so if you have any questions, please let me know. Have a great day.